So let's continue with our design process here. We were looking at how to recognize the elements that have failed during the design process. And you can see that those beam or column elements that are failing will be displayed in a red color. As you can see here, these beams are being displayed in red colors here, whereas these columns are all in pink colors. So these beams, they are in red color, means they are failing. So let's go to 3D view and let's go to this display design info option and then go to identify all failures, apply. If you choose this output option, identify all failures, then the type of failure that is present in your model will be displayed here. So what I would like to do is, let's see the design results for one of the beams that is failing here. For that, go to elevation view at any elevation here. For example, I will go to this elevation view A here, and in this display design option, select the rebar percentage and then click on OK. You can see that the reinforcement percentage is being displayed for these beams here, for this beam, for this beam, for this beam, and yet the beam is displayed in red color. So right click on any one of these beams and then go to these details here. The ETABS concrete frame design details will be displayed here, and if you scroll down to the bottom, what you will see is that shear stress due to shear force and torsion together exceeds maximum allowed. So our beam is failing in shear here. So remember that when our beams are failing, but these reinforcement percentages are being displayed like this here, then you have to understand that our beams are failing in shear and not in flexure. In contrast, if the beams are being displayed in a red color and instead of the percentage of reinforcement here, this OS, that means the overstressed result is being displayed as OS like this, then you have to understand that our beam is also failing in flexure. So the reinforcement percentage is displayed and the beam is failing, means the beam is failing only in shear here. So if our beam is failing only in shear, then how can we correct for that? For this, let's go to the beam design details again. So I will right click on this beam here. I will go to this details and then I will go to the shear details at the top here. And if we scroll down and go to the bottom and go to this shear rebar design here, you can see that our shear limiting capacity, that is tau C max, is 3.1 megapascal, whereas the shear stress that is coming onto our beam is 2.66 megapascal. So there are two conditions here. Remember, if this tau C max, the value of tau C max is greater than the value of T, which is our case here, tau C max is greater than the value of T, then we have to design the shear rebar for our beam based on this design shear force, which is 287.0254. And if you open any reinforced concrete design structure book, then there are 5 or 6 steps for the design of shear reinforcement. Use this value of shear force and design for the shear rebars in our beam. This is first condition, in which tau C max is greater than T here. In contrast, in second condition, if the value of the shear stress T is greater than tau C max, then you have to change the section of your beams. And particularly what we do if our beams are failing in shear in that way is we will increase the width of our beams. So remember these two steps. If the limiting value tau C max is greater than T here, you will design shear rebars for this shear force here, whereas if the value of shear stress T is greater than tau C max, then you will have to increase the width of your beam. In that case, you can design for the shear rebar, and hence you can make your members pass during or under shear forces also. So that is the way to check for shear force and shear design in beams. If it is failing in flexor, then you have to, if it is failing in flexor and this overstress messages are being generated here, then in that case you have to increase the depth of the beam. So you can see that not almost all of our beams are failing in shear here. Since there is no overstressed message, the reinforcement percentages are being displayed here, but the beams are red in color. These beams are failing in shear again. And you can design for shear rebar in the way that we discussed just now. And after beams, if you look at columns, the columns are not failing in our structure or in our model here. All of our columns has passed. You can see here. So let's go to this display design info option again, and let's check on this column PMM interaction ratios. Apply and OK. So these columns are being displayed in pink color, means that the capacity of these columns is being utilized from 90 to 100%. If the capacity of these columns are being utilized in greater than 100%, then these will fail and these will be displayed in red color here. But only about 92 or less than 100% of the capacity of the column is being utilized. So these columns are being displayed in pink color here. If you want to do a more conservative design and you want this capacity to be utilized to a lesser value, that means between 70 and 90%, then you can increase the sectional size of these columns also. So let me do that for now. What I would like to do is, let me just unlock this model, go to define section properties, frame section. I will change this column 500 by 500 to column 600 by 600 and see what happens. I will change this depth value to 600 and then width value also to 600, and I click on OK. Now I will analyze the model and then I will design again and see what capacity of the column is being utilized. What is the utilization factor for these columns in our structure? So let's wait till the analysis is complete here. You can see at the bottom the model cases are being analyzed here. After the design of this beam and column, then we will go to the design of shear walls. And in design of shear walls, we will look at three types of design method that are available in ETABS, and we will use one of those methods for the design of shear walls. So our analysis is complete. Now then, click on this concrete frame design and the design process will start. Go to 3D view and go to display design info as column PMM interaction ratios. So still these are being displayed in pink color, so let's leave them as it is. As you increase the sectional size of these columns, then less and less capacity of these columns will be utilized. So utilization factor will decrease and correspondingly the color of these columns will also be changed. Now since our columns are not failing here, we will not make any further changes. So we will assume that our sectional size are also correct here. One thing that you can notice is after you increase the size of the columns, the rebar percentage will decrease here. So just to make comparisons, once you use the 500 by 500 size columns and check the reinforcement bar for certain columns and then increase the column size in the next step and run the analysis and design process again and recheck the reinforcement percentage for those columns. You will find the changes, and in this way, by changing the size of these columns and beams, you can optimize for the design of your structure. So in this way you can design beams and columns. Now let's go to the design of shear walls. So before going to the shear walls, I would like to display only shear walls here. So what I will do is select properties and wall sections, basement wall and shear wall. I will select these wall sections here, and then I will right click on our model and then click on show selected objects only. Our shear walls only are being selected here. So now to design shear walls, first we have to assign the pier sections to these shear walls. So after the analysis is complete in ETABS, we can first select all of these shear walls here. We can go to design and then shear wall design option and then assign pier sections. And in this assign pier section, there are three different options for design. One is the Simplified Cnt Design, which is the compression and tension design. Another is the uniform reinforcing, and another is the general reinforcing. Let's look at in a little about all of these three pier sections or these three design types. First, the simplified Cnt design or the simplified compression and tension design is used for the design of planar walls. And using this option, you can only design your shear walls. You cannot check for the design of your shear walls. So in this option, the pier geometry is defined by the length, thickness, and sizes of each member at each end of the pier. And the program will report the required width of the edge strip. After you perform the design, the program will report the required width of the edge strip to resist the axial and overturning moment and the reinforcing required for resisting those loads. So the simplified Cnt design method is used for the design of shear walls, whereas in uniform reinforcing design, this option is applicable either to design the planar walls or to check for the design of our planar walls. Check means you will assign the value of reinforcement for those shear walls and you will check if those reinforcement is sufficient or not. And then in general reinforcing, we will use section designer to assign general reinforcing for our shear wall. For today, we will use this option uniform reinforcing. So our pier material here will be M25. Let us suppose that the bar size for our distributed bars is 20 mm and these will be kept at a spacing of 150 mm. The clear cover for rebar, let's leave it as 25 mm, and also the end or corner bars will be size 20 mm. And finally, you have to check this option. Either you want your reinforcement to be checked, that means the reinforcement that you have just inserted here, either you want to check for this reinforcement or you want the reinforcement to be designed. For now, I would like that the reinforcement is to be designed and then click on OK. Now after assigning pier section, let's go to the design, shear wall design and view a revised preference. The design code will be IS456. The multi-response case design, we do not need this since this option is for nonlinear static pushover analysis. And you have to change the rebar material here also for the design of shear walls. So change this to HYST500, HYST500, and other options, leave those default values and then click on OK. Go to the shear wall design option once again and then now select design combinations. Again, we will use the same design combinations. Select these combinations and click on this arrow pointing to the right. Now these are our design combinations and then click on OK. Finally, go to this design shear wall design and then start design check. Now our shear walls have been designed here. Let me just look for any one particular shear wall. Suppose I want to look for this shear wall here, or let me just look for one particular shear wall. Okay, let's look for this shear wall here. I will just right click on this shear wall, and there we have the ETABS shear wall design data. So here we have different options and different information given here, including the pier details. Here we have the length of our shear wall, 1823.3 meter. We have the thickness of our shear wall, which we defined while defining the section properties for wall, which is 200 mm. And then we have this flexural design here. For example, let's look here. We have top reinforcement, we have top reinforcement is 3354 millimeter square, and the bottom reinforcement is 1399 millimeter square. So let's see here how this reinforcement or this rebar is distributed in our shear walls. Let me just open my whiteboard. Okay. Let's remember that our area of rebar is 3354 millimeter square. It is 3354 millimeter square. Remember that this area of reinforcement is for two faces of our shear walls. If I draw the section of our shear wall, then this is our shear wall here. We have rebars on both faces, on this left face and on this right face here. And then these longitudinal reinforcing bar are supported or enclosed by these shear rebars like this. So this is the section of our rebar. So this 3354 represents the reinforcement for these both faces, left face and right face. So for one face, the area of reinforcement will be 3354 divided by 2. How much do you get? 3354 divided by 2, you get 1677 mm square. This is for one face. Now suppose that we are using 20 mm dia bars here. You know that the area of cross section for 120 mm dia bar is 201 mm square. So you have the total reinforcing area required in one face and the reinforcing and the area of one rebar. So if you divide this 1677 by 201, you will get the number of rebars required in one face. So let's divide this by 201. You will get 8.34. 8.34. That means you have to use 9 rebars in one face. For example, for this left face you will use 9 rebars, and for this right face you will use 9 rebars. So we will have 9 number of 20 mm dia rebars on one face. And then you can calculate the spacing of reinforcement based on this data yourself. For example, if our clear cover for this is 40 mm, and if we are using 8 mm dia rebars for shear reinforcement, then spacing you can get it this way. For example, first, what is the length of our shear wall? First, find the length of our shear wall. The length of our shear wall is 1823.3 meter. So 1823.3 meter. This is the length of our shear wall. And from this, subtract the clear cover on two sides, which is 2 into 40 mm, and then subtract this shear reinforcement from both sides, 2 into 8 mm, and finally, since the diameter of these bars is 20 mm, 20 by 2 on one side and again 20 by 2 on one side. Now you got this spacing of this inside part here from the center of this bar at one end from to center of this bar at another end, and divide it by the number of bars, 9 minus 1. So how much will you get? Let me calculate this. So you will get the spacing of reinforcement bar is 213 mm. So since this spacing of reinforcement is a little bit larger, if you want to decrease this spacing and increase the number of rebars, then you can decrease the diameter of rebar to be used here and instead use 16 mm dia rebar. So this is how you calculate the longitudinal reinforcing in your shear wall. Get this value of reinforcement from your ETABS data, divide it by 2 to get the value of reinforcement in one face, and then find the number of rebars on one face by dividing this area by the area of one rebar, and then find the spacing based on this diameter of rebar that you will be using and the clear cover in your shear wall. In this way, you can design the shear walls from ETABS. So this is for flexural design, and similarly you can design for shear also. If you see here, we have the rebar area is 500 millimeter square per meter in case of shear walls. So this per meter means this is 1 meter height of the shear wall here. Just don't be confused. If it is flexure, then you have to see this section here, but in case of shear, you have to see this section here. If this is the elevation view of our shear wall, then you have to select this 1 meter distance along this height of the shear wall here, and along this 1 meter distance we have to design the shear reinforcement such that the area of the shear reinforcement is 500 millimeter square. In this way you can design for both the shear wall in flexure and shear reinforcement for our shear walls. So now we have completed the design of beam, column and shear walls in ETABS. In our next lecture, we will be dealing with the design of mat foundation. Since we have a basement here, we will be dealing with design of mat foundation in SAFE software. So we'll see you again soon, or we'll meet again soon in that next video lecture. Till then, stay safe. Bye bye.